We've reached a new level in our calculus learning. We are looking at antiderivatives, which are just the inverse of a derivative. So this statement right here is just basically saying that we are an antiderivative is when we undo a derivative. Okay, so we're going to look at this first example. If f of x is equal to 3x squared, what is the antiderivative of f? So if we think for a second, what would I need to take the derivative of to get 3x squared? What I need to take the derivative of is something like x to the third power. So the derivative of x to the third power is 3x squared. So we can say that dx of x cubed is equal to 3x squared. So we're undoing, it's as if we already took a derivative. How would I undo that process? Okay, so one thing to notice is that when there are other examples of functions that I can take the derivative of and get a derivative of 3x squared. For example, I could have y is equal to x cubed plus 1. So dy dx is equal to 3x squared plus 0. Oh, same derivative. Okay, let's do another one. Y is equal to x cubed plus pi. Dy dx is equal to 3x squared plus 0. Another, y is equal to x cubed minus 7. Dy dx is equal to x cubed, oh, not x cubed, 3x squared minus 0. So notice here that on each one of these original functions, I have some kind of constant that I added to my x cubed term. And when I take the derivative of that, I get a 0. So the problem with an antiderivative is that we don't know what this term is that we could potentially add on to our function, to the part with the x. So we don't know what that constant is. So it's important to remember that an antiderivative of a function is not an antiderivative or the antiderivative. There's actually infinitely many antiderivatives of a function. I know that sounds crazy. Okay, so what this means is that when we take the antiderivative, so we're going to go ahead and do that for 4x to the third power. And the way we do this is we take the antiderivative of 4x to the third power would be, I'm going to raise the power up 1, so x to the fourth. And then I take my constant, what that was already there, and I divide by whatever power there was. So the antiderivative of 4x to the third would be x to the fourth. But again, if I take the derivative of x to the fourth to get 4x cubed, like there's a whole bunch of different equations I can write. I can add any constant I want to that equation. So to show that, what we do is we add a constant of integration. So when we take a antiderivative or an integral, we have to add that constant of integration because we don't know what number was originally there. Okay, so what we have is finding an antiderivative is called antidifferentiation, or in this case, it's called an indefinite, taking the indefinite integration. So anti-differentiation and indefinite integration are the same thing. Okay, so let's break down what this business looks like. We just took the antiderivative of 4x cubed. Officially, how we need to write this is we are saying we're going to take the integral, okay, of 4x cubed with our variable of integration being dx, okay? And what we got was our original function of x to the fourth plus our constant of integration. Break this down a little. This sign here is the integral symbol or operation. Okay. Inside is the integrand, and the dx tells me the variable of integration. Okay. The c on the outside is our constant of integration, which we need for any indefinite integral. There are two types of integration that we do, indefinite and definite. So when we take an indefinite integral, we have to add that constant of integration. All right, here's some basic rules. They are highlighted for you on page 250 or also in the front cover of your book. We're going to take the integral of 0 dx. So if I remember correctly, if I have a derivative that equals 0, it's because I started with a constant line. So what this equals is 0x plus our constant of integration. So I have no x's, and then so I could take, let's say, for example, let's work backwards. Let's say I had 0x plus 4. The derivative of 0x plus 4 would be, well, the derivative of 0 is 0, and then the derivative of 4 is also 0. This number, c, the constant of integration, could have been any number, 5, 7, 8. It just depends on what point the integral is going through. That's it. Okay. So if I have the integral of a constant, okay, then I am going to end up with kx plus c. So an example of that would be like the integral of 7 dx is equal to 7x plus c. So if I just look at, if I took the integral, the derivative of 7x, I would get 7. The integral of the derivative of a constant is 0. Okay. And next up, I have k times f prime of x. Anytime you have a constant, you can move it out as a scalar out to the front of the integral. Okay, times the f prime of x dx. And the derivative of f, the antiderivative of f prime, so the antiderivative of a derivative, I know that's gross, sorry, is just f of x. That's your original. F of x dx, and then we, oh, no, not the dx. F of x times k. And then don't forget, you could have some kind of constant out there. All right, if I have two functions, the integral of f prime of x plus g prime of x, well, the antiderivative of a derivative would just be f of x plus the antiderivative of a derivative would be g of x plus our constant. Lastly, this is if we have a power. So like, for example, x to the integral of x to the 7th. There's a invisible 1 out here. Okay, dx. What I would do is I would raise the power, so x to the 8th. So that would be like x to the n plus 1, since our original power was n. You take what was already out as the coefficient, so 1, and you divide by the power. So I'm going to take my 1 and divide by n plus 1. Or you can also write plus c, or you can write this as x to the n plus 1 over n plus 1. All right, I forgot my plus c here. Okay, this is an example. Let's do some more examples. Oh, I know. This rule right here is super important. We've seen this before in reverse. This is reverse power rule. Okay. Let's do some examples. So we're going to integrate the following to find the antiderivative. All right, so I have the integral of 3x dx. So we're going to take the integral with respect to x. And I have a so we can actually just take the integral here. I have a power of 1. I could move this 3 to the outside if I want to write 3 times the integral of x dx. That's totally fine. So let's do it that way. We're going to bring down the 3. We're going to raise the power, so x to the 2nd power. And then remember, you have to divide by that 2nd power plus c. So I get 3 over 2 x squared plus c. All right, next up, integral of 1 over x squared dx. We shall rewrite this as the integral of x to the negative 2 dx so that I could use my power rule. All right, so we have to raise our power by 1, so x to the negative 1, and then we divide by that power. And the coefficient from the original stays the coefficient, but we divided by the power. So this gives me, of course, we have to add our plus c. I have negative x to the negative 1 plus c, which is equal to negative 1 over x plus c. Okay, next up. Again, let's rewrite t to the 1/2 power dt with respect to t. So we're going to raise our power, since I have a power rule here, I have t to the 3/2. I had a 1 out in front as the coefficient originally, so I'm going to divide by 3/2. The faster way to do this would be if my power is a fraction, I'm just going to multiply by the reciprocal of 2/3. So instead of dividing by 3/2, I'm multiplying by the reciprocal of 2/3. And I'm going to add my plus c. Number 4. Okay, so if you have a polynomial, we need to make sure that the polynomial is sandwiched between the integral and your between the variable of integration. And to make it really clear, we usually put it in parentheses. Okay, so this is y plus 2 is what I am taking the integral of. And so we take, in a polynomial, you take the integral of each piece separately when I'm adding the pieces together. Okay, so I have y to the 1st power, so it's going to change to the 2nd power, and I'm dividing by 2 to match the power, plus 2. I technically have y to the 0 power, so this is going to change to y to the 1st power divided by 1, add my c, and simplify. Y squared over 2 plus 2y plus c. Okay, number 5. So polynomial, the integral of 2 theta squared minus 3 theta plus 1 is d theta, so with respect to theta. So I'm going to start by just writing 2 theta cubed divide by 3, so I always raise the power by 1. Whatever the power is, that's what I'm dividing by. Okay. Minus 3 theta to the first power changes to the second power over 2, plus this is theta to the 0 power. So 1 theta to the first power over 1 plus c. So just simplify 2/3 theta cubed minus 3/2 theta squared plus theta plus c. Okay, last one. So we're going to take the antiderivative, underivativeness. Okay, this is gross looking. Let's change it. This is x plus 1 over x to the 1/2 power dx. We're going to divide this x to the 1/2 power into the numerator since I'm dividing by a monomial. So powers, I subtract them. So x to the 1 minus 1/2 would be 1/2, and then plus x to the negative 1/2. And I'm taking the integral with respect to dx, to x. Okay. All right, time to integrate. So when I integrate, I can drop the sign. So I do the integral sign. So I go x to the 3/2. Remember, when I'm dividing by a fraction, you're really going to multiply by the reciprocal. Okay, so 1 times 2/3 plus x, raise the negative 1/2 by 1 power, so to the 1/2 power. The reciprocal of 1/2 is 2, so we're going to multiply by 1 over 2 plus c. So I end up with 2/3 x to the 3/2 plus 2x to the 1/2 plus c. All right, so just to prove to you that this actually works, let's take the derivative. We're going to take the derivative with respect to x of 2/3 x to the 3/2 plus 2x to the 1/2 plus c. All right, so we multiply. 2/3 times 3/2 is 1, so that's x. And then, so 1x to the subtract 1 gives me 1/2, plus 2 times 1/2 is 1, so 1x to the negative 1/2, plus the derivative of a constant is 0. So I get x to the 1/2 plus x to the negative 1/2. And so do we matchy matchy? Look, matchy matchy. When I use these antiderivative rules, that actually gives me the original function. Okay. All right. Or what we're thinking about is the original function. It's the antiderivative. Okay. That's it. We're going to look at trig integration next. Trig integration.